Welcome to BYJU'S Exam Prep, India's most comprehensive exam preparation platform. Myself Dinesh. So in today's session, we're going to discuss wonderful concept, a tricky concept you can say, and a very important concept as well. So the concept is binary symmetric channel. So I'll be discussing this concept in detail, very detailed. So in today's session, we'll be discussing the concept behind it, the basics behind it. So in tomorrow's session, whatever we discuss today, whatever is the concept that we understand today, based on that, whatever problems are possible, that we'll do it in tomorrow's class. And some models of problems, we'll do it in day after tomorrow's class. Okay. Right. So before starting with the session, let me introduce myself for the sake of new students. So I have 10+ years of experience. So I've done my master's from IIT Madras, and my specialization of master's is communication systems, and that is my subject of expertise also. The subjects that I teach for GATE and ECE are communication systems and signals and systems. And this is my Telegram group, Electronics by Dinesh Gutha. So if you wish to ask me any doubts on communications or signals, you can follow me on this group. And if you wish to ask me any general questions regarding colleges or any other general guidance, if you wish to ask, you can just definitely contact me on this group. I'll be ready to help you. And I have cracked GATE twice. Right, so that is my intro. So what we will be doing in today's session. So agenda of today's session is first, I've given you, one second. So first we will talk about homework questions. Whatever homework questions I've given you in yesterday's session, I'll discuss the answers for them very quickly. And after that, we'll talk about a binary symmetric channel, today's concept, very important concept. We'll spend most of our time on this. So after discussing homework questions, we'll deal with this. And after that, I'll give you some homework questions, because today only concept will be over, but I'll be giving you 1 or 2 questions based on what we have understood today. Right. So understand carefully, this is very tricky concept, but I'll make it I'll make sure that it will be very easy at the end of the session. Right, so these are the homework questions. So 4 questions I have given. So let me quickly give you the answers. So how to do them, I'll do quickly, so you should be able to understand from what I'm going to explain. But the procedure for all these kinds of models is given in yesterday's session. In yesterday's session, all these models were discussed in very detail. The concept behind it is also discussed. So in today's session, since these are homework questions, I'm just going to quickly provide the solutions. So message signal is sampled at 100% higher than Nyquist rate. So sampling rate is 100% higher, which means 2 times of Nyquist rate, which is equal to 2 times of bandwidth. Bandwidth here is 1000 pi, means the frequency there is 500 hertz. So which is 2 kilohertz is the sampling frequency, or 2 kilo samples per second also you can say. Next, sampling rate we know, and encoded using a delta modulator. Find the optimum value of step size so that slope overload distortion is completely avoided at all instants of time. So if you want slope overload distortion to be avoided, we know the condition. Since it is sinusoidal signal, the condition is AM into omega m is equal to, should be less than or equal to. Since they are talking about optimum value of step size, yes, we can talk about equal to condition. If you put equal to, we'll get the optimum value of step size to avoid only slope overload distortion, delta by Ts. This implies AM we know it is 10, and omega m is 1000 pi. 1000 pi is equal to delta optimum into 1 by Ts. 1 by Ts is Fs, and Fs we know it is 2 kilo. 2 kilo, if you substitute 2000, you can cancel these 3 zeros and 3 zeros here. 2, if it comes to this side, it will be 10 pi divided by 2 is 5 pi. So delta optimum is equal to 5 pi volts. The answer is 5 pi volts, which is 5 into 3.14. 5 3 is 15, 14 5 is 70. So which is 15.7, approximately around 15.7 volts. Answer is 5 pi volts. Okay, so coming to the next question. A message signal m of t is equal to is encoded using a delta modulator. So when they give this kind of signals, first let us plot the signal. We have discussed this model of problem yesterday's session also. If you missed yesterday's session, you can watch out for it after the session when you get time. So let us plot this one, 4t. an increasing signal, and 4t is like it exists from minus infinity to plus infinity, but it is multiplied with a rectangular signal which exists from 0 to 3. And next this signal is multiplied with the another rectangle signal from 3 to 6. So this signal exists only from 3 to 6, and the slope of this signal is minus 4. So if you plot this part, it will be something like this. And what is the height here? At t equal to 3, 4 3s are 12, height will be 12. So this is how the signal, message signal looks like. So what is the slope here? Slope here is 4 units, and the slope here is minus 4 units. What are they asking about? Is encoded using a delta modulator. The sampling rate used in the delta modulator is 400 samples per second. Is it possible to design an optimum value of step size so that there is no distortion? Is it possible? Designing optimum value of step size is possible only if magnitude of slope is constant in whatever time it exists. The time in duration in which it exists is 0 to 6. Within the first 6 seconds it exists. In that duration, is slope constant? No. We don't want slope to be constant. We want magnitude of slope to be constant. Magnitude of slope here is 4, and here also it is 4. Magnitude is 4. Right? Since magnitude of slope is constant, the answer is yes, we can design an optimum value of step size so that there is no distortion. Right? So if so, what is the optimum value of step size? Let us write the condition. D by dt of m of t modulus maximum is equal to delta by ts. This is the condition to find the optimum value of step size. Right. So what is this slope? We know that the value of magnitude of slope is 4 units is equal to delta optimum into 1 by ts is fs, and what is that sampling rate? It is given as 400. So delta optimum is equal to 1 by 100 or 10 millivolts. That is the answer. So let's go to the third one quickly. A message signal m of t equal to 20t is encoded using a delta modulator. The sampling rate used in the delta modulator is 200 samples per second. Is it possible to design an optimum value of step size so that there is no slope or there is no distortion by the delta modulator? What is the condition? Magnitude of slope should be constant. So if you find the slope here, slope for m of t, if you find the slope for m of t, slope is 20, so magnitude of slope is constant. If magnitude of slope is constant, yes, it is possible to design an optimum value of step size. The answer is yes. If yes, we want to find the optimum value of step size. So d by dt of m of t modulus maximum should be equal to delta by ts, delta optimum divided by ts. This implies, what is the magnitude of slope here? We know it is 20 units. It is equal to delta optimum into 1 by ts is fs, and how much is given as fs? 200. So from that we can understand delta optimum is equal to 20 and 200 cancel, it becomes 1 by 10 or 0.1 volt. 0.1 volt is the answer. Coming to the next one, a message signal m of t equal to 80 into this one and this one is encoded using a delta modulator. Same funda, same question, similar question. The sampling rate used in the delta modulator is 500 samples per second. Is it possible to design an optimum value of step size so that there is no distortion? Is it possible? It is possible only if magnitude of slope is constant. Let us see if the magnitude of slope is constant or not. Just by look of it also we can say, but let me plot it and show you. As a function of t, let's plot the signal 8t, a signal with slope 8. A signal with slope 8, and that exists from 0 to 2. It exists from 0 to 2. And what is the height at 2 seconds? At t equal to 2, the height is 16. The height is 16. Okay, next. Let us plot the next part. 8 minus t into u of t minus 2 minus u of t minus 2 4. This is a rectangle from 2 to 4. This exists from 2 to 4, that much we know. Now let us just look at this part. 18 minus t, the slope is minus 1. The slope is minus 1. And definitely we know that it is a straight line. For a straight line, if you can plot 2 points, you can plot the straight line. So let us plot the first point. At t equal to 2, if you put t equal to 2, if you substitute t equal to 2 here, 18 minus 2 is 16. At t equal to 2 seconds, the amplitude of this signal at 2 seconds is 18 minus 2 is 16, the same amplitude, same point. Okay, so this straight line, the first point is this point, which is 16. Next, let us find the last point, then we can connect them at t equal to 4. At t equal to 4, how much is it? 18 minus 4 is 14. So it is 14 here. At t equal to 4 seconds, it is 14. Don't think that it should be a triangle signal like this. It's not like that, because the slope here is -1, whereas the slope here is 8 units. Okay, and after t equal to 4 seconds, there is no signal that is existing in the given equation. So after 4 seconds, it is 0. So that's why we can connect it like this. So the slope of this part of the signal is only 1 unit, -1 units. Is the magnitude of slope constant? Yes, no. Is the magnitude of slope constant here for this signal? The slope here is 8 units and the slope here is -1 units. So magnitude of slope here is 8, magnitude of slope here is 1 unit. Is the magnitude of slope constant in the duration of time in which it exists? It is not constant, because it's different, no? It is 8 here, it is 1 here magnitude. Since it is not same, it is not possible to design a step size so that there is no distortion. It is not at all possible. If we design the step size according to 8 as slope, then we'll have a problem here, we'll have a distortion here. If we design a step size according to slope as 1, then we'll have a problem here. So it is not possible to avoid the distortion. Okay, very good, Sanjay. Right, these are the answers for yesterday's homework. These are homework questions which I have given you yesterday, 4 questions. If you have not solved it previously without looking at the answers, you can solve it and you can cross check your answers. Okay, very good. So let's move on to the today's topic. Guys, today's topic is a wonderful topic, and I have learnt it with great difficulty, because when you study textbooks, you'll not get the idea that I'm going to teach you, because I have developed that idea after putting a lot of effort. It takes time to get that understanding, so I'm going to give you that understanding. If you understand it that way, then whenever you see this model of problems, it becomes very easy. I'll tell you, at the end of this session, you'll find the easiest way to answer this kind of question. Hardly 1-2 minutes, you should be able to solve most of the questions based on binary symmetric channel. So let us start. Right, binary symmetric channel, or particularly I'm talking about binary channel. Binary channel is like a more generic term. Symmetric channel is a subset of this. Whenever you see a graph like this, right, you might have seen this graph in multiple places, but in communication, there is only one area in which you see this kind of graph. In signals and system, there is one place, which is FFTs. In FFT, we draw some butterfly diagrams. This also is looking like a butterfly diagram, but this is not, we are not talking about FFT here. In FFT, we talk about the flow of the, in FFT, whatever is the FFT algorithm saying, that we represent in graphical format, in this format. But here we are not talking about FFT. Here we are talking about channel. Ones and zeros we transmit through the channel, right? Ones and zeros we transmit as voltages. At the receiver, these voltages, because of noise, they change and will be received as something else. Okay, this channel is talking about, we are talking about communication channel. Okay, right, I'll explain in detail what is happening here. So let me name the inputs x0, x1. This is like input we are sending corresponding to 0 bit. This is like input corresponding to 1 bit. And similarly, what we receive here, let me call it as y0 and y1. This is a communication channel, and we are talking about 2 input, 2 output communication channel. Whatever analysis we are going to do for 2x2 channel, similar analysis can be extended to higher order channels also, 3x3, 4x4 kind of channels also. Same concept, nothing will change. Okay, why is this always changing? Come on, stay here. Right, So we're talking about communication channel. So whenever you see this kind of diagrams in communications, so the problems involved are based on binary channels. Okay. So if the channel is symmetric, which means if the channel behaves equally in the same way for 0 bit and 1 bit, we call it as binary symmetric channel. Okay. If the channel does not behave symmetrically, we call it as binary asymmetric channel also. But symmetric or asymmetric together, I am calling it as binary channel. So now our discussion is based on all of them, all the binary channels together, binary symmetric, binary asymmetric, all of them. Okay, right. So observe carefully. Very interesting and very important topic. You should not miss a point. You should be very focused. Remove all the distractions which you are having right now and keep focused on this. Right. So what is the meaning of x0, x1 and what is the meaning of y0, y1? Before getting into the analysis of this diagram, and when they give you this diagram in any problem, what is the data they are going to give you? What is the data they are going to give you? And using that data, what kind of questions they are going to ask us? All those details we'll discuss little later. Okay. Before that, first of all, let us get a feel of, okay, what is this x0, x1 and what is this y0, y1? Let us try to understand that first. Okay. Let us try to understand that first. Okay. So the understanding behind inputs and outputs of binary channel, this x0, x1, y0, y1, what are they exactly? How to have a what is the common sense idea of what is this x0, x1, y0, y1? Instead of blindly saying x0, y1, x0, x1, y0, y1, we should have some clarity, right? What are we talking about? So let me give you that clarity here. What I mean by x0 is, so in digital communication, we transmit the possibilities, zeros and ones, or we might also transmit higher symbols also, like multiple zeros we combine, and we can transmit it m array schemes. If you remember, we can transmit m symbols also in a channel. We can transmit m symbols also, right? Not only 2 symbols, we can transmit m symbols also. But let us talk about the simplest case. We talk about 0 bit. 0 bit is transmitted as 0 bit. Can you transmit a 0, a number 0 through a channel, a wireless or a wired channel? How do we transmit 0? Because we're going to transmit as a voltage, right? If you're going to transmit 0 through a wired channel, how do we transmit? A wired channel can only communicate voltages, right? An electrical channel, an electrical wire kind of channel, like coaxial cable or twisted pair cable, these kind of cables, or Cat4 cable, Cat5 cable, I mean the LAN cable. So all these carries a signal in the form of electrical pulses. They don't know the numbers, okay? They don't know the numbers, they only know the voltages. So for the wire to carry information, if you're putting this 0 bit into a wire, what we are going to do is, we can't put that number into the wire, we can only put the voltage corresponding to it, voltage representing it. So 0, we are going to transmit with some voltage x0, and 1, we are going to transmit with some voltage x1. Something like this is like -5 kind of volts, -5 volts. Just for your understanding, I'm just giving you some voltages, okay? -5 volts and +5 volts. Is that okay? I hope everybody is following. x0, x1. Just for your understanding, let me say this is something like example sake, I'm taking it as -5 volts, and let me say for example sake, I'm taking this as +5 volts. Okay, right. Now x0, x1 are like the voltages corresponding to 0 and 1. Now as x0 is transmitted through the channel, through a wired channel, when you transmit through the channel at the receiver, okay, the noise gets added. Because of the noise, will the voltage change or not? Noise also gets added in the form of voltage. Whatever is the voltage that the channel is carrying, and at the receiver whatever is received, that gets added with the noise. The noise voltage will change the original voltage. So we are supposed to receive -5, but instead of -5 we might receive -5 plus noise, something like n of t or n of t, let's say. Similarly, when you transmit +5 through the same channel, we should be receiving, we are expecting +5 without noise, but because of noise, we are receiving +5 along with 5 noise also will be added. And how much is that noise? We don't know. Noise voltage is not fixed, no, it is random. It is random in nature. Random means it takes different voltages. At one, let's say at t equal to 0 seconds, it might take a voltage of +1. At t equal to 2 seconds, it might take a voltage of +2, -2, -0.5, +0.5. At different times, it takes different voltages because noise is a random process or a random signal, which means it is random, which means we can't predict how much is the voltage taken by it. But it will take some range of voltages, okay? Right. So because of noise, what happens is, we are supposed to receive -5, but because of noise, we might receive any voltage, let's say from -10 to, or else -15, let me say the maximum. Let me assume that noise can be between -10 to +10. Let me assume, okay? It's not, that's not a, noise cannot be that big. With very less probability, it can be big. Noise voltage can be big, but with very, very less probability. Why? Because it is a random signal. I'll just give you some idea of that also. Noise will have, come on, there is some problem with this board. It is troubling us. Right. Noise is Gaussian, we know that much, right? Additive wide Gaussian noise. We're talking about noise only, na? As a function of n, noise, this is the PDF of noise, Fn of n. So the probability that noise will be 0 only 0. Yes, it can be 0 with some decent good probability, The probability that noise will be smaller, it is with higher probability, but with small probabilities, noise can be very big also. Okay, noise can be very big also, which means, let me assume that it is something like -10 here and +10 here. Okay, so noise can be anywhere between -10 to +10. For example's sake, okay, noise can't be that much big. It can't be +10 volts, no chance. Noise cannot be that big. Just for your understanding, proper understanding, I'm telling you -10 to +10. Okay, right. Sir, if noise is not -10 and +10, then why are you taking that example? You might ask me. Yes, because see here there are many assumptions that we have. So I'm trying to make it simpler. Okay, so why noise voltages and signal voltage generally they are close. We'll design the system according to that way only. Because when you send -5 volts, do you think that we're going to receive only -5 volts? No, na. Because of channel, attenuation will happen. This -5 volts might be received as -5 millivolts or microvolts. The voltage that is received will be very, very small. Okay, whatever is the order in which the signal voltage is received, in a similar order, like if it is in millivolts, if it is in microvolts, noise voltage is in the range of micro or nanovolts. Okay, they are of similar order. So that's why, since I have taken this in volts, I am taking noise also in the range of volts only. Okay, so don't get confused. Okay, there are whatever points are supposed to be understood, just try to understand them. If they are having any other questions, any ambiguities here that I have explained just now, if you're having any such ambiguities, you can ask me. I would be happy to answer them. Okay, but first focus on what is the point that I'm going to convey. Our idea, what is that we want to understand in this slide? We want to understand what is the meaning of x0, x1 and y0, y1. Once we understand that, then we'll talk about binary symmetric channel. Okay, right. So, come on, man. Wait, let me close this once and open it again. Okay. Now tell me this, -5 volts, right? But noise, minimum voltage on noise is -10. So -10 plus -5 is -15. -10 plus -5 is -15. That is the least voltage possible. When 0 bit is transmitted, we transmit -5. But because of passing through channel, noise gets added. Because of noise, what is the minimum voltage possible? The noise plus signals combined, what is the voltage that we are going to receive? -10 is the least here, -5, total -15. What is the highest voltage possible? -5 plus 10 is +5. Correct? That is the range of voltages possible. Next, +5 plus n of t. This noise is added to this, or same noise is added to this. Minus 10 plus 5 is minus 5. Minus 5 to, what is the highest voltage possible for noise? 10. 10 plus 5 is 15, right? So if you observe, the voltages possible here are minus 15 to 5, and the voltages possible here are minus 5 to 15. There are some common voltages. There comes the problem. You are confused now. Okay, if there was no noise, no confusion. If you receive minus 5, yes, I'll say that okay, 0 is received. If you receive plus 5 without noise, if there is no noise, there is no confusion, I'll understand that it is 1. But now the confusion happens. Okay, what are the voltages that we are going to receive? Minus 15 to, minus 15 is the starting voltage, and plus 5, come on man. Minus 15 is the starting voltage, and plus 5 is the ending voltage. These are the voltages that we receive. And what are the voltages that we receive here? The voltages that we receive here are minus 5, minus 5, minus 5 to plus 15. So this is the common region. If you receive any voltage from minus 5 to plus 5, okay, so once if you are passing anything through a channel, if this is channel, you transmit something. What you transmit, receiver does not know. Receiver only will receive some voltage, one of these voltages, minus 15 to, total voltage possible are from minus 15 to plus 15. 0 and 1 together, minus 15 to plus 15 are the voltages possible. Among those voltages, we might receive some voltage, something like, let's say 10 volts. After looking at 10 volts, what will we decide? What shall we decide? 10 volts is possible only when 1 is transmitted. Okay, we can clearly say that, okay, 1 might have been transmitted, right? So if you receive minus 10 volt, here we are very clear, okay, 1 is transmitted. Okay, and here we are very clear that 1 is transmitted. How about minus 10? Minus 10 is received, minus 10 is received only when 0 is transmitted. We are very clear here also, no confusion. But how about 0 volts? How about minus 1? How about minus 2, minus 3, minus 4? All these voltages, for all these voltages, is there a confusion or not? Because when you receive 0, 0 can be received because of transmission of 0 bit, correct? And 0 can be received because of transmission of 1 bit also. When you receive 0 volt, you are confused. Is it because of 1 or is it because of 0? We are confused. Yes, there is a confusion. Definitely, when at the receiver, when you see the voltages, we will have confusion. Okay, by looking at that confusion, we should design a criteria. We should design a criteria to get the best performance. Because there is a confusion, we have to make some decision. Okay, by looking at some voltage, we have to decide. We have to decide it as either 1 or 0. We have to make some decision. Without making a decision, how will you get the bits at the output? If you are confused and you stopped, because I am confused, I'll stop understanding whether it is 1 or 0. You stop understanding, you will not receive the information. If you want to receive the information, whether it is correct or wrong, you have to do something about it, right? You have to do some kind of detection. By looking at the voltages, detecting the bits by looking at the voltages is what we call as detection criteria. The best criteria that does the job is what we call as MAP criteria or ML criteria. Maximum a posteriori probability criteria or maximum likelihood criteria. We'll talk about that in today's session only. Okay? Right? Okay, observe carefully. Okay? Right, so I hope you are following. If you receive any voltage between minus 5 and plus 5, is there a confusion or not? There is a confusion, right? So, when there is because there is a confusion in any practical communication system at the receiver, definitely there will be confusion. Because there will be some common voltages received because of 1 volt and because of 1 bit and 0 bit, whatever voltages we are supposed to receive, in those voltages at the receiver, there will be some common region, that common voltages. So, when you see any voltage between minus 5 and plus 5 at the receiver, if you see any voltage between minus 5 and plus 5, there is a confusion. So you have to avoid that confusion, you have to make some criteria, you have to make some decisions. And how will be that decision? What I'll do is, generally what we do is, we'll draw some midpoint. We'll draw some midpoint and we will say, to avoid this confusion, anything above 0, we'll understand it as 1 bit. Anything below 0, we will understand it as 0 bit. So should that be the only criteria? No need. The criteria need not be like that. Criteria can be different. If you want, you can frame your own criteria. But will that give the best performance? That is the question. Finally, what we want? We want the bits to be received correctly, which means with high quality. That is our criteria, right? So if you are able to, if you decide some criteria, if let's say Sanjay is deciding some criteria, and if that is giving very good quality, that's fine, perfectly fine. Okay, but we can't do every now and then we can't design a criteria, right? So that's why somebody has designed a criteria called map criteria or ML criteria. If we can follow that criteria, definitely we can do the best detection possible. We can get the best quality possible, right? Okay, I hope you have understood. Now, why not is something like this? Why not? Why not means it's something like this. Why not means, in this case, why not means what? Detection because of 0, you can say. All the voltages, give me a second, let me ask this video team guys to resolve this. Just wait for a few minutes, okay? I'll continue the class. Just keep trying to understand what I have just now discussed. I'll be back in a minute. We'll correct that issue. Okay, I think now it should be resolved. Okay, right. So why not means, in the binary channel, what do I mean by why not y1? That is what I'm trying to explain. Just for the sake of explaining why not y1, I have told you all this story. So why not means it's voltages, any voltage greater than, sorry, less than, right? Yeah. Any voltage less than 0 volts. Why not is like any voltage greater than 0, something like that, which means 0 to 15. 0 to 15, why not is not a single voltage, why not is like a range of voltages. Mind this, why not is like a range, okay? It's not like a single voltage. The range of voltages which are responsible for zero detection, you can say. The range of voltages which we look at, when we look at those voltages, we are going to treat it like a detection of 1 bit. Okay, y0 and y1 are not single voltages, whereas input x0 and x1 are like single voltages definitely. Because of noise, definitely you are not going to receive single voltages. You will receive a range of voltages. For 0 bit you receive a range, and for 1 bit we receive another range. Okay, so the range of voltages that we use to detect as 0 bit, that we are calling it as y0. The range of voltages that we use to detect 1 bit at the receiver, we call it as y1. I hope you're following. This is the practical thing. This is a very practical thing. So this is what we do in our digital communication receiver. So matched filter receiver, if you take, in matched filter receiver, yes, we do exactly this. We use map criteria, ML criteria. In today's class also we'll talk about map ML criteria. In when you do probability of error derivation. Here also we'll talk about probability of error, but in binary channel the probability of error is little bit more simplistic. We'll deal it in a superficial manner, but the concept is correct only. Whatever concept we discuss here and in the original probability of error derivation matched filter area, that is, the concepts are similar, but in probability of error derivation using matched filter, there we go into the depth of the concept. We use the noise, PDF, everything we use. There all the concepts are used. So we are not going to get into that discussion, matched filter discussion in today's session, but any problem based on binary channels can be solved using the concept that we learned in today's session. But whatever we are going to learn here will help you in much better understanding when we talk about matched filter receivers. Okay, and the probability of error derivation, based on which multiple questions were asked in the last 4 or 5 years. Multiple questions were asked, and based on this binary channel also, many questions were asked in the last 5 or 10 years. Many times questions were asked. Right, I hope everybody got an understanding of what is the meaning of y0, y1, x0, x1. Is that okay? Can you respond? Right. Now, once we have understood x0, x1 are the voltages corresponding to 0 bit and 1 bit, the voltage that we have transmitted for 0 bit and 1 bit, and y0 and y1 are also voltages, but it is not a single voltage, but they are like some range of voltages. The range of voltages that we receive, this is one range of voltages, this is another range of voltages. As per the previous example, this is like 0 to minus 15 to 0, and this is like 0 to 15, something like that. Some range of voltages, another range of voltages. Okay, very good. Now let us discuss everything in detail. So corresponding to this 0 bit, whatever is the probability of 0 bit, same will be the probability of voltage corresponding to x0. So the probability of x0 or the probability of 0 bit will be given in the problem, or some information will be given about it. Similarly, we are having probability of x1. At the input, only 2 possibilities are there. So we know the basic property of probability, and what is that? Total probability is equal to 1. At the input, what are the possibilities? Only 2 possibilities. If you add up the probabilities of both of them, should it not result in 1? It should result in 1, right? So let us write this here. Let us write our basic observations based on our basics of probability. P of x0 plus P of x1, it should result in 1, definitely. Similarly, see this one, at the output also we are having only 2 possibilities, y0, y1. Which one we will receive? We don't know. Output is also random in nature, input is also random in nature. Because they are random, we are having probabilities. So y0 will have certain y0 happens with certain probability, y1 also happens with a certain probability, right? So P of y0 and P of y1, if you add them up, what is the result? It should be definitely 1, right? Very good. We are just writing our observations. These observations are beautiful observations, simple observations, but all the observations that we are going to make, that will help you to develop everything that we are going to develop in this session. Simple observations only. So on these 4 lines, some probabilities will be given. Whenever they give you binary channel, they will give us some probabilities here, and those probabilities are conditional probabilities. Okay, conditional probabilities will be given. So here on this line indicates transmitting x0 and receiving some voltage corresponding to y0. Transmitting x0 and receiving y0. Conditional probability for this to happen, it is P of y0 given x0. This probability. And similarly, on this line, whatever probability is given, they may not give you in an exam or in any question. They'll not give you. They'll give you some probability here, but you should understand whatever probability they give on this line. Okay, they're talking about on this line we are having x0 and y0. They're giving us y given x probabilities. Whenever they give you binary channel, and whatever probabilities they give on these lines, they are giving y given x probabilities. In y there are 2 possibilities. In x there are 2 possibilities. Okay, on which line they are giving, based on that you can understand what value of y given what value of x. On line, whatever is given is y given x probabilities. On this line, it is y0, and another one is x0. So it should be whatever is given here is y0 given x0 probability. Similarly, on this line, whatever is given is y1 given x1 probability. y1 given x1 probability. Next, on this line, on this line whatever is given is y given x probability, which is y naught on this line given x1, and on this line whatever probability is given, that is p of y1 given x naught probability. So what this graph is discussing is the probability of receiving y naught given that under the condition that x naught is transmitted. If you know that you have transmitted x naught, if you have transmitted x naught, because of noise you might receive y naught, a voltage is some voltage here or in some voltage here. Because of noise, x naught need not be received as y naught only. It might be received as y naught or it might be received as y1. The probability with which it happens, that is given here. Given that x naught is transmitted, once you know that x naught is transmitted, what are the possibilities that can happen? Y naught or y1. Once you know that x naught is transmitted, the condition is x naught. See this one, from among these two, the condition is x naught. Once you know that x naught is transmitted, the two possibilities that you can receive is y naught, y1. If you add the probabilities of receiving y naught, y1 when x naught is given or when x naught is transmitted, those two probabilities when you add, will it result in 1 or not? See this one, p of y naught given x naught, given that x naught is transmitted, one possibility is receiving it as y naught and another possibility is receiving it as y1, and if you add both of them, it should definitely result in 1. If you randomly add some two conditional probabilities, it will not result in 1. Okay, let's say I'll just make it clear with another example. So for example, there are 3 lines starting from x naught. Let's say it's a 3 by 3 channel. Instead of 2 by 2, let's say 3 by 3 channel, x naught, x1, x2, y naught, y1, y2. Then from x naught, one more line will be there to y2. Given that x naught is transmitted, there are 3 possibilities, y1, y naught, y1, y2, if it is a 3 by 3 channel. Then adding these two will not result in 1 because that is not complete. Okay, because when you transmit x naught, there are 3 possibilities in a 3 by 3 channel, y naught, y1, y2. Then if you add p of y2 given x naught, then only it will result in 1. But in this graph, yes, these two are sufficient because when x naught is transmitted, there are only 2 possible outcomes, which is y naught and y1. Okay, I hope it is clear. Right. Similarly, when x1 is transmitted, there are only 2 possible outcomes, y naught, y1. Similarly, when x1 is transmitted, there are only 2 possible outcomes in this graph. So if you add these two probabilities, given x1, there are only 2 possible outcomes, y naught, y1. If you add the probabilities of those two, that also should result in 1. P of y naught given x1, the condition should be same, y1 given x1, that should result in 1. If somebody asks you y naught given x1 plus y naught, y1 given x naught, here the condition is not same. If the condition is not same, this need not be 1. Sir, is there no chance it will be 1? It may be 1 sometimes, but we can't guarantee because the condition is different. When you add these two probabilities, we can't say whether it will become 1 or not. Mostly it will not be 1 only. Mostly it will not be 1. Okay, we can't guarantee this. We can't guarantee that it will be 1. So there is no point of writing this. We can't guarantee that this will be 1. But when the condition is same, you're talking about only the case of where x naught is transmitted or x1 is transmitted. Okay, I hope you're following. I've transmitted 0 bit. Okay, if I transmit 0 bit, I'll transmit as x naught. I might receive it as y naught or I might receive it as y naught, y1. If you know that x naught is transmitted, if you clearly know that x naught is transmitted, when you know what is the meaning of condition? When somebody says given x naught, what it means is once you know that x naught is transmitted, the probability of receiving y naught, that is what is p of y naught given x naught. P of y naught is only the probability of y naught without information of what is being transmitted. P of y naught given x naught is you have some information and the information is somebody told you that x naught is transmitted. You have that information. But even if you know that what is being transmitted, you will not know what is being received. Given that you know some information that x naught is transmitted, the probability that y naught is received or y1 is received, those are these probabilities. P of y naught is without any idea what is being transmitted, whatever is the probability of receiving y naught, that is P of y naught. There is a difference, we have to observe it Understand it carefully. Right, so this we can't say anything about this, whether it will be 1, mostly it will not be 1. We can't say anything about this. Very good. Similarly, I'll write something else also. Those probabilities we are not here, but some other conditional probabilities. X0 given Y1 plus given Y1, same condition. How about this one? Can anyone tell me the answer for this? Given Y0, the meaning is you have some information that I have received Y0. I have some information that Y0 is received. Okay, Y0 is received, but because of what it was received? Y0 can be received because of X1 or because of X0. Because of any of these two, we can receive this. If you have some information that Y0 is received, then you're talking about this condition. The probabilities that you talk about when you know some information, and the information is Y0 is received, then you're talking about these probabilities. Once you know some information, you can't talk about the individual probabilities, we have to talk about conditional probabilities. Once you have the information that Y0 is received, it might be because of X0 or it might be because of X1, and they happen with some probability, and that probability is these things. Given Y0 is received, there are only two possibilities that can result in Y0. There are only two possibilities that can result in Y0, which are X0 and X1. Because there are only two possibilities, if you add them, it will result in 1. Let's say if it is a 3 by 3 channel, if there are 3 lines ending at Y0, if there are 3 lines instead of 2 lines, if there are 3 lines ending at Y0, then you have to add three probabilities. Instead of X0, X1, you have to add B of X2 given Y0, then only it will become 1. All the possibilities. Given that Y0, what are the things that are responsible for Y0? How many things are there? You have to add the condition probabilities of all of them. That only will result in 1. It's not like always only these two probabilities, if you add it will be 1. It's not like that. If it is a different channel, it's a 3 by 3 channel or 4 by 4 channel, then you have to add more things. Okay, you have to add all possibilities. The basic property of probability is sum of probabilities of all possibilities should be 1. Okay, here given Y0, only 2 possibilities are there. We are adding those 2 possibilities, which will result in 1. If it is a 3 by 3 channel, given Y0, there will be 3 possibilities resulting in Y0. If you add those 3 probabilities of those possibilities, that will result in 1. Okay, I hope it is clear till this point. Right. So we have some very basic observations about this. Okay, now let's get to the interesting part. Which is map criteria or ML criteria. So what is our job here? We have transmitted some voltages. Instead of ones and zeros, we have transmitted voltages, and because of noise we are receiving some voltages, and there are some common voltages also. Now we have to make some decision. What is the decision we have to make? By looking at the received voltage. You have to look at the received voltage. By looking at the received voltage, you have to make a decision. Either I should decide it as 0 or I should decide it as 1. Sir, can I decide it correctly? You may not be able to decide it correctly always, because there are common voltages. Right? See this one? Observe carefully. Let's say you have received it as 0 volts. Okay, you can make a decision as 1 or 0. Let's say I'm making a decision as 1. But 0 volts can be received because of 0 bit also. But when it is received because of 0 bit, I'm making an error. That's fine. When you're making decision, you will be wrong sometimes. That's fine. But you should be wrong the least number of times. If you are wrong least number of times, then we have least probability of error. Okay, when we are making decisions here, by looking at voltage, we are making a decision as 0 bit or 1 bit. When we are making these decisions, we need not be correct all times. It is not possible to be correct all times. But if we are wrong only minimum number of times, the least number of times possible, that is the best detection criteria. The criteria which will have very less wrong decisions, that we call it as optimum criteria or best criteria, the criteria which gives least probability of error. Right. Now let's talk about observations in binary channel. We have done that. We have done it here itself. These are the observations. Next, let me talk about map ML criteria now. Map means maximum a posteriori probability criteria. Okay, and ML, what is ML? ML we call it as maximum likelihood criteria, which is just a subset of map criteria. So what is maximum likelihood criteria? It is a map criteria only. Map criteria when P of x0 and P of x1 both are same. When the input probability is 0 and 1 probability is same, then map criteria is exactly same as maximum likelihood criteria. Okay. Sometimes in the problem they will not give us P of x0, P of x1 probabilities, and they just simply say maximum likelihood criteria. We should understand that, okay, they have given the probabilities. If they are saying maximum likelihood word, it means they are talking about these probabilities to be equal. If those probabilities are not equal, then we are not talking about ML, we are talking about map. So map, special case is ML. Map talks about all types of probabilities. P of x0, P of x1 can be anything. Any combination of P of x0, x1, map addresses that. Okay. In that, a special case where these two are equal, that case we call it as ML. Okay, both are same criteria only, but this is a special case where the probabilities of inputs are equal. Okay, wonderful. Now let me go back. Okay, see this one. So there is something called a priori probabilities, prior probabilities. What are those? Prior probabilities. What are those prior probabilities? Can you say? Prior means before transmission. Before transmission, what we have is x0, x1. What are the probabilities that we have before transmission? The probabilities that we have before transmission are P of x0 and P of x1, right? Now, so these are prior probabilities. That's why we call it as a priori probabilities. Priori, that is the word that they have used in textbook, but simply you can call it as prior probabilities. Similarly, prior, the opposite of prior is posterior. Or a posteriori probabilities. What are these a posteriori probabilities? A posteriori means after transmission is over. After transmission is over, the combination of x0, y1 probabilities, the conditional probabilities of x0, y1, those we call them as a posteriori probabilities. And what is that? What are those probabilities? Given y probabilities, all the given y probabilities. Once the transmission is over, we will know what is being received. We are able to look at the received voltages. Once we know what is the received voltage, if you talk about the transmitted voltages, given that you know received voltages, those are a posteriori probabilities. The probabilities which talk about a posteriori probabilities also talk about input voltages, but knowing the information that what is being received. Hope you are understanding. Prior probabilities means before transmission happens, the probabilities of the inputs. A posteriori probabilities are also probabilities about the inputs, given the condition that we know what we have received. We know what we have received. Under the condition that we know what we have received, what is the probability of input being transmitted? Those probabilities we call them as posterior probabilities. Probabilities of inputs, given the condition that we know what we have received. So P of x0 given y0, or P of x1 given y0. Since there are only 2 by 2, it's a 2 by 2 channel, there are only 4 possible probabilities like this. P of x0 given y1, P of x1 given y1. These four probabilities we call them as a posteriori probabilities. Okay, I hope it is clear. Conditional probabilities only, but these are not the conditional probabilities that will be given in the binary channel, right? I hope you have observed this. So the probabilities given in a binary channel are not x given y probabilities, they are y given x probabilities. These are not same as a posterior probabilities. But these two have a relation, na? Y given x and x given y, they have a relation. You might have learned it in probability theory, right? We'll just recollect that basic. Okay. So these we call them as a posterior probabilities. But these are not readily available. But map criteria, map talks about maximum a posteriori probability criteria, na? Which means map criteria is based on these probabilities. Map criteria is based on these probabilities. So map criteria, we'll first write it based on these probabilities. But the probabilities available for us are y given x probabilities. But we know there is a link between these two. Using that link, we can get the relation, map criteria relation in terms of y given x probabilities. That is possible, right? So first of all, let us understand this. Let me write something here. Can anyone tell me what is the relation between P of A given B and P of B given A? P of A given B and P of B given A. So P of A given B, you know that we can write it as P of A intersection B divided by P of B, right? So let us multiply and divide with P of A. Let us multiply and divide with P of A. So these two we will combine. So if you combine, we will get it as P of B given A, correct? P of A intersection B divided by P of A. In the denominator it should be P of A. So P of B given A, if you expand it, is P of A intersection B divided by P of A into P of A divided by P of A. It's a very simple relation. If you forget it also, you can get it back easily. So this is the relation. I'll tell you a very simple observation here. A given B can be written in terms of B given A. Okay, A B given B can be written in terms of B given A very easily. So B given A, if it is here we are going to multiply diagonally opposite. A here we are going to multiply with P of A in the numerator. B here in the numerator will be multiplying with P of B. Similarly, you can write P of B given A in terms of P of A given B. These two you can bring it onto this side. You don't need to by heart anything. You don't need to by heart anything. These are very simple things. You can get it on your own. Right. Right. So using that basic, can anyone tell me how to express P of y naught given x naught? All these four probabilities I want you to express in that format. So P of x naught given y naught, how to write it? P of y naught given x naught, P of y naught given x naught into P of x naught. See this one? Whatever is in the denominator, that write in the numerator. Whatever is in the numerator, write it in the denominator. See this one? Similarly, P of x1 given y naught, reverse it, y naught given x1 into x naught, x1 here in the denominator, so write it x1 in the numerator, y naught in the numerator, write it in the denominator. Similarly, you can write it, you can take this as a homework, P of x naught given y1 and P of x1 given y1. So these two also similarly express it. This is your homework. Okay, a simple homework. Right. So I'm moving ahead. I'm moving to map criteria. So we have talked about a posteriori probabilities just now. We have talked about a posteriori probabilities, right? Once now that we have all the basics that is required, now let us talk about map criteria. Okay, talking about map criteria is as good as talking about ML criteria also. Right. So what is map criteria used for? By looking at y naught or y1, by looking at the output of the receiver, by looking at the voltage that we receive at the receiver, by looking at that, I should make some decision. Okay, this is that decision criteria. How to make a best decision by looking at the output voltage. Okay, in the receiver. Okay, I'm at the receiver, so I'm receiving some voltages. I'm receiving some voltage. First 5 volts is received. Okay, by looking at the 5 voltage, I have to make a decision. Next, after a few seconds, I'll receive another voltage, 10 volts. After, by looking at that, I have to make a decision. How to make a very good decision? If we can use this criteria, if we can just follow this criteria to make those decisions, We'll make errors sometimes, but we'll make least number of errors. But if you randomly make some decisions, you might make more errors. So which means the communication will not be of good quality. If you want the communication to be of good quality, error should be as less as possible. If you want errors to be as less as possible, your decision should be appropriate. Your decision should be more times correct. Okay. So this criteria, map criteria, is a decision criteria. Detection means decision. Detection of bits, or making the decision of bits by looking at the voltages. So this criteria, if we follow this criteria, we can make the best decisions possible. Best decision does not mean we don't make the wrong decisions. We make wrong decisions, but it is possible only very, very less number of times. Okay. Now let us talk about the criteria. Observe carefully, very, very carefully. P of x naught given y naught. Let's take a posteriori probabilities. When you take a posteriori probabilities, the received, see, we have to make a decision by looking at the output, na? So that's why we know the output. We are having in our mind the output. We are looking at the output. We have to make a decision about the input. Since we know the output, the given condition is output is known. So that's why I'm talking about map criteria talks about given y naught probabilities, because we know the output, right? We know the output. Given that y naught is received, it can be received because of x1, or it can be received because of x naught. Correct? Y naught can be received. Okay, let me plot the diagram quickly here. Observe carefully. You have observed that y naught is received at some point of time. When you're observing, y naught is received. After that, y1 might be received. After that, y naught might be received. Okay, you might receive y naught, y1 alternatively, or many times y naught, sometimes y naught continuously, sometimes y1 continuously. You might receive them in any manner. But let's say at some point of time, when you looked at the output of the receiver, you have observed y naught. When you have observed y naught, and if you observe y naught is because of what? Who is responsible for y naught? Is x naught responsible for receiving y naught, or x1 responsible for receiving y naught? Because the lines are drawn like this, it means that x naught is also responsible for y naught, or x1 is also responsible for y naught. But we don't know exactly who is responsible at that point of time. At that point of time, when we have observed y naught, who is exactly responsible for y naught? We don't know. Okay, so how to know that? We don't know. We will definitely not know. Finally, we will not know whether it is because of x naught or x1, we will not know. But we know that both of them are responsible. Okay, but we have to make a decision. We have to make a decision. Okay, it is because of x naught, it is because of x1. We have to make some decision. But we don't know exactly. At any point of time, we don't know definitely, because it is probability game, na? And we receive y naught because of x naught with some probability. With some probability means it's not certainty, na? We might receive it sometimes, we might not receive it sometimes because of x naught. We might receive it because of x1 sometimes. Right? Observe carefully. This is little tricky. Once you understand it, everything will be clear. See this one? 100 times you are transmitting x naught. Okay? Or else I'll do it the reverse way. When you receive y naught 100 times, you have observed y naught being received 100 times. And you have observed carefully. Let's say 70 times it is because of x naught, and 30 times it is because of x1. Observe carefully. 30 times it is because of x1, and 70 times it is because of x naught. Now tell me, by looking at y naught, if you decide it as x naught, if you make a decision that by looking at whenever you receive y naught, if you say that okay, x naught is received, you have to make some decision, na? Let's say your decision is to make you decide it as x naught. Then how many times are you correct? Can anyone answer? By looking at y naught is received, you have seen that, and you are having only two options: make a decision as x naught or x1. Only one of them. We can't make both, right? You have to make some decision, because you have to decide there's one bit or 0 bit. Which decision is more appropriate? Let's say if I make a decision as x naught, how many times am I correct? Because of x naught, I'm going to receive y naught 70 times, which means I'm correct 70 times, but I'll be wrong 30 times. Because 30 times I'm going to receive y naught because of x1. Out of 100 times, 30 times we receive y naught because of x1 also. Okay. Sir, I can make those 30 times as decision as x1, but how will you know that? We will not know that. Once you receive y naught, well, let's say y naught is some voltage, let's say 5 volts. By looking at 5 volts, how will you know it is because of x0 or x1? We will not know. We will never know. So whenever you look at 5 volts, make the best decision possible. So if you make the decision as x0, you are correct 70 times and you are wrong 30 times. There are only two decisions possible, deciding it as x0 or deciding it as x1. Now let's decide it as x1 and see. If the decision is to decide it as x1, then what? If you decide, whenever you decide y0 as x0, then you are correct 30 times, but you are wrong 70 times. Only two decisions are possible. So 30 times correct and 70 times wrong. Only two decisions possible, either this one or this one. Which is the best decision? Which is the best decision? If you take the decision as x0, whenever you see y0, based on the probabilities, since instead of probabilities, to make it easy, I have given some numbers. Okay, 100 times you are receiving 70, 30. Just I'm giving just for the sake of understanding it more easily. Okay, but this is the final idea behind the probabilities also. If you are receiving y0 with more probability or more number of times because of x0, the best decision to make is x0, because you will have least number of errors. See this one, only 30 errors. But if your decision is opposite, if you are receiving y0 because of x0 30 times, and if you decide it as x0 only, when you receive see y0, if you make a decision as x1, you are correct 30 times, but you are wrong 70 times, because those 70 times you are receiving it because of x0. We want to be correct more number of times. We can't be correct all the time. We can't be correct all the time. We can only be correct most number of times. Okay. Practically, we will not be wrong 30 times. We will not be wrong. We will not design the system in that way. We will be wrong 1 out of 1 lakh times or 1 out of 1 million times. That might be the case, general. It's not like 30 times error, sir. 30 times means we can't bear it. The quality is gone. Then there is no chance. Just for the sake of understanding, I'm telling you this. Okay. Similarly, y0 also. We can also understand y1 also in the same manner. Let's say y1 is received 100 times. And you received that because of x1 70 times and because of x0 30 times. Then when you see y1, if you decide it as x1, you are correct 70 times and wrong 30 times. And if you decide it as x0, you are wrong 70 times. So the best decision is the decision which gives you more number of correct detections or less number of wrong detections. As simple as that. Are you following? Right, I hope this part is clear. A very simple example I have taken. This should be easily understood. If there is any confusion, just go back through this part of the lecture again. Okay, it will be more clear. If there is a confusion, I believe you might have got it already easily. Right, same thing. Instead of numbers, I'm talking about probabilities. Probability is also a number, na? Probability is like the highest value is 1. Percentage means the highest value is 100. Okay. So probability is like the highest value is 1. Instead of 70, we call it as probability as 70 by 100. It is 0.7, something like that. Instead of 70, we write it as 0.7. So that's the only difference between those numbers and these probabilities. Now, if I put this relation, what is the decision criteria? Tell me what is the detection criteria? Decision criteria or detection criteria. DC means detection criteria. In short, I am calling it as DC. Okay. See this one, what is the meaning of this? Given y0 is received, we are receiving y0 more number of times because of x0 itself. That is the meaning of this condition. Sir, it will be greater than? We don't know. Based on what probabilities they have given us, we will compare and we will see. If the probabilities are behaving in this manner, what it means is, given y0, you are receiving y0 more number of times because of x0. So what is the best decision to make? You tell me. Decision criteria is, whenever you see y0, whenever you receive y0, what is the best decision to make? The best decision is, what is the input because of which you receive this y0 more number of times? Because of y0, we are receiving y0 because of x0 more number of times, because it is greater sign symbol here. Greater sign is here because the probability of receiving y0 because of x0 is greater. So the best decision to make is y0 implies x0. I hope you're following. This example is exactly according to this. 70 na? We have given that y naught is received, you are receiving it more number of times because of x naught. When it is like 70-30, this is the condition na? This is what happens, this is the relation between these two. But in the example I have taken, this is satisfied. But if I take some other example, this 30 and this 70, then different thing will be satisfied na? The relation will be different. Same thing, same posterior probabilities. Let's say the condition is less than. According to this, it is condition is this greater than sign will be acceptable. But if it is like 30 here and 70 here, 30 here and 70 here, it means when you receive y naught, it is more number of times because of x1 when there is 70 here. Correct? So this sign is also possible. Which of them is possible? Practically anything is possible. Okay, so which of them will be possible in a particular problem? See, they will give you, they'll give the information about probabilities na? Based on those probabilities, we have to see and check which is happening. Either this might happen or this might happen. Both will not happen na? Only one of them will happen. So based on the information in the given problem, we can understand either this relation is being satisfied or this relation is being satisfied. So let's say if this relation is being satisfied, then what should we do? What is the decision criteria? Tell me. What is the decision criteria? Decision criteria is, what is the decision criteria? When you receive y naught, we are receiving y naught. By looking at y naught, what is the best decision to make? You are receiving y naught because of x1 more number of times, because probability of receiving y naught because of x1 is greater. So the best decision to make is, when you receive y naught, decide it as x naught, make a decision as x1 because the probability of receiving y naught because of x1 is greater than receiving y naught because of x naught. So this is the best decision to make. See, the decision changes. So the decision is different. The best decision is different when the probabilities are differently distributed. When the probabilities are different, when the relation is different, the decision is different. So in the given problem, observing which relation is being satisfied, based on that we have to make the decision. Okay, don't think that's a 0 here, 1 here. It's not like that. It's just notation. Na? Y naught is some set of voltages. X1 represents some bit voltage that we have transmitted for 1 bit. Y naught is some set of voltages. Sir, 0, y naught means x1. Is that not possible? Yes, it is possible, definitely. Very good, Sherry. Right. Similarly, we have understood about y naught. By looking at y naught, how to make a decision, that we have written. And this is what is a map criteria. Whatever conditions I have written here, this is what we call as map criteria. Okay. Next, how about same way? Let us talk about y1. Okay. Given y1, by looking at y1 at the receiver, let us make a decision. By looking at y1 at the receiver, let us make a decision. Okay. If you want to make a decision, you should know the relation between these probabilities. If you should know the relation between x given y probabilities. Let's say if this is happening, what does that mean? What is the meaning of it? Just understand the meaning of it. Given y naught, given that y1 is received, you are receiving y1 more number of times because of x naught, because the probability is greater. Because the probability is greater, the meaning of it is you are receiving y1 with more probability because of x1. We are receiving y1 because of x1 with more probability compared to receiving y1 with x0. You are receiving y1 with more probability because of x1 compared to y1 receiving because of x0. The probability of this happening is more compared to this. So what is the best decision to make? The decision criteria is y1 implies, when this relation is being satisfied, the best decision to make is whenever you see y1, decide it as x0. That is the best decision to make. That will give you less number of errors. Similarly, that's last one. Given y1, when you see y1 at the receiver, and if you compare these probabilities and the relation is satisfied is like this. The meaning of this is, try to understand the meaning of this. Looking at y1, if this is happening, the meaning of it is you have received y1 and you are receiving it with more probability because of x1 than x0. You are receiving y1 because of x1 with more probability compared to x0. So what is the best decision to make? You are receiving y1 with high probability because of x1 compared to x0. So best decision to make is, whenever you see y1, decide it as x1 for higher correct detections or least number of wrong detections. As simple as this. This is what is map criteria. This is what is map criteria. The same basics we use it in matched filter receiver also to derive the probability of error formula. Okay, here also we'll derive probability of error formula, but we'll do it, just do it for a 2x2 channel case from binary channel perspective. In matched filter receiver, we do it in a different way, more mathematical way, but the concept is same. I hope it is clear till this point. So now, we can write these two together. We can write it in many textbooks. You might find this kind of relation. So these two together, we can also write like this. Okay, right. So these two, sometimes you can also write these two combine, these two equations you can combine and write it. And how you can write it is P of x0 given y0, P of x1 given y0 greater than, less than. Any of these two might happen. If greater than happens, what is the decision making? x0. If it is greater than, the decision making is x0. When you see y0, if this is satisfied, decision making is x0, and when this is satisfied, the decision making is x1. These two and the decision criteria together in a single line in more simpler format. So you might see this kind, greater than, less than, both signs, and on top of it they'll write the decision making also. So this is one way of representation. These two lines together along with the decisions we can write in a simple format like this. So in textbooks, if you to see something like this, or in any material if you see something like this, try to understand the meaning of this. Whatever we have understood here, same thing is conveyed here. If it is greater, then decision making is x0. If it is lesser, the decision making is x1. And similarly, these two also we can write now. P of x0 given y1 greater, lesser, P of x1 given y1. Can you quickly tell me? So what is the decision for greater sign? x0. Whichever is greater, that symbol we have to write. x1 is greater here, and when this is satisfied, x1 is the decision. Okay. So these two lines together, whatever I have written in these two lines, it is exactly same what we have written here, but we can write it in this manner also. Okay, I hope it is clear till this point. Is it okay? Okay. So Mr. Sherry, can you be more clear on what you're asking? So you are not, you don't need the concepts that I'm teaching, definitely, right? For your grandchildren, you're asking, so what are they studying, and what are their ambitions? What do they want to pursue? So if you can be more clear, I can be of more help. Right, so these conditional probabilities, x given y conditional probabilities, we can also write them in terms of y given x. Na? We know the relation between P of A given B and P of B given A, right? Using that, we can change these conditions into other conditions, right? If you can change it, then only we can use it, because what is given in a binary symmetric channel? P of y given x probabilities are given. So in a binary symmetric channel, what is given? P of y naught given x naught probabilities are given, not x naught given y naught, that is given. Okay, from this we can find these probabilities. Yes, that is possible. Instead of that, why can't we change this map criteria? Why can't we change this map criteria into y given x probabilities? We can do that easily, no? Correct? Right, we can do that easily. So this is P of y1 given x1, and this is p of y1 given x0, and this is p of y0 given x1. Right, now let us rewrite these things. So these two lines together we can write it like this, these two lines together we can write it like this. Let me use this so that we can save some space. So this one, p of x0 given y0, how do we write it? X0 given y0 we can write as p of y0 given x0, this thing into p of x0 divided by p of y0. See this one, is that okay? Everybody understood? P of x0 given y0, I have written it as p of y0 given x0 into p of x0 by p of y0. I hope everybody understood. We have discussed that in the previous slide. See this one? We have understood. We have discussed that in the previous slide. We have discussed the basic behind it. Okay? I'm just using that basic. Similarly on the right hand side also, p of y0 given x1 into p of x1 divided by p of y0 greater than, less than x0 x1. Same thing, I'm just copying. So this x given y probability I'm converting into y given x probability. Now see this one, there is some cancellation here that is happening. There is some cancellation that is happening, right? Now let us combine this, p of y0 given x0 into p of x0. How do we write that? Yes, we can just stop it at that place. P of y0 given x0 into p of x0 greater than, less than p of y0 given x0 into p of x0. See this one, how the map criteria is converted? For y0 reception, map criteria is converted into this format, very simple format. Is converted into y given x probabilities which are completely available, and p of x0, p of x1 also are available because they are prior probabilities which are also will be given, right? Now in a similar manner, how to write this one? See this one, this also we can convert now. P of y given x1, x0 given y1 can be written as p of y1 and given x0 into p of x0 by p of y1. If you write it that way, in the same manner, just do it. You can try it back. I'm just writing the direct thing because we're talking in terms of y1, p of y1 given x0 into p of x0 in the same format. This also write it in the same format and apply it. You'll be getting something like this. y1 given x0, x1 into p of x1. One second, I think I have written a small mistake here. Given x1 here, given x1 here. Okay. I hope everything is clear till this point. We have talked about map criteria. The map criteria we are trying to convert, same map criteria we are trying to convert into y given x probabilities. As simple as that. I hope this part is clear. I hope this part is clear. Now these two conditions, yeah, map ML decision criteria. Let me just rewrite them once again. P of y0 given x0 into p of whatever I have written in that corner for y0 reception, and for y0 reception, what is the other possibility that we transmit because of for y0? x1. When y0 is received, it is because of x0 and x1. Greater than symbol, less than symbol. When the greater than sign is satisfied, it means x0 is the right decision to make. When less than sign is satisfied, x1 is the right decision to make. Okay. Now you can also rewrite this, right? See this one. P of A given B can be written as P of A given A intersection B divided by P of B. So P of A intersection B can be written as P of A given B into P of B. The conditional probability into whatever is the denominator. If you multiply with the probability of that, then you get the intersection probability. Intersection probability. Intersection probability means the probability of transmitting A and receiving B. You don't know any information prior. Okay, you don't know any information prior. There is a probability of transmitting A okay, and receiving B, whatever probability that happens, that is what is intersection probability. So this one also we can write it as, it is looking like P of A given B into P of B. We can write it as Y naught intersection X naught. This total thing we can write it like this. Same analysis, everything same. We're just modifying this using that basic. P of Y naught intersection X1. See this one? Beautiful relation. It looks very simple now, right? So if a Y naught is received because of X naught more number of times than Y naught is received because of X1, then the best decision to make is X naught, because the probability of receiving Y naught because of X naught is more. And similarly the other thing also. Similarly, can we write the other result also? P of Y1 given X naught into P of X naught, whatever I have written in the previous slide at the end, that I am writing it here, greater than, less than, don't worry, things look little complicated, you might be understanding, but things might be looking little complicated. I'll simplify everything. Okay, just keep understanding whatever I'm talking about. At the end, once I derive all the formulas, I'll just show you that binary channel, that butterfly diagram, and we'll make everything look easy, very easy. Okay, I promise you that much. Things will look very, very easy at the end of the session. Because whatever we are writing, when we are writing mathematically, they look little complicated. If there is something that you did not understand, it might look very complicated. But at the end, once I show binary symmetric channel and we'll apply all this on the channel, binary symmetric channel, that butterfly diagram, and things will look very, very easy. Okay, I promise you that much. ECE branch, how much I prepare communications, sir, IITs interviews. See, for electrical branch, you don't need communication, right, Mayank? For especially IITs or IIT interviews, nobody will expect you to have good knowledge on communication. I mean, if you are talking about communication subject. Communication system subject for electrical students is there for ECE, engineering services. If you are preparing for engineering services, then only communication systems subject you have to study, that too analog and digital communication. You don't need to study the total communication, only analog communication and digital communication part we have to study. You can leave random variables, random process and noise analysis. Okay. And for IITs, for an electrical student, nobody expects you to have knowledge on communications. Okay, you can leave it. Okay, so we got the conditions. Let us write the final condition here. So we can write this as P of Y1 intersection X naught. Y1 intersection X naught we can also write as X naught intersection Y1. Anything is fine. Order is not important here. X naught is the decision here. X1 is the decision here. And here this is Y1 intersection X naught. So this one, finally, this is what is map criteria. Map criteria when you are analyzing Y naught, map criteria when you are analyzing Y1. These two conditions together, that is a map criteria to make a decision by looking at the received voltage. As simple as that. Now, ML criteria. ML, maximum likelihood criteria, means P of X naught is equal to P of X1, no? Right? So this implies, what is ML criteria? See this one? From this and this. If P of X naught and P of X1 are same, that is a special case, in map criteria only, there is a possibility of these two becoming equal, no? Then this and this will cancel out. These two will cancel out, right? If these two get cancelled out and these two get cancelled out, the conditions will become much more easier to understand. So the conditions will become P of Y naught given X naught greater than, less than, say this thing I am copying, these two we can cancel if these two are equal. Similarly, the other condition. So when somebody suddenly comes and looks at this, they think that this is very, very complicated stuff, but this is not that much complicated. Okay. Oh, wonderful. So though you are from electrical, you are watching my communication lectures. I'm very happy to hear that. So if you are interested in communication, you can write ECE paper also, GATE ECE paper also, because most of the subjects are common. If you are interested in preparing communications, though you are an electrical student, you can prepare communications, and ECE and electrical, only once communications is the complete subject, that is not common for ECE and electrical. Apart from that, EDC, whatever you study in electrical, that is compared to that, in ECE there is a little higher syllabus, and EMT also, whatever syllabus you study, compared to that, little higher syllabus is there. These are the only changes. It's hardly like 150 to 200 hours of extra preparation. Communication is one complete subject which is not there for electrical, and EDC, EMTL are there for electrical students, but for ECE students, slightly higher syllabus is there. How you prepare? Watch my lectures. Just, you don't need to study any textbook, just watch my lectures completely. You'll be able to answer most of the questions, and if you are lucky, if there is no very tough question kind of thing, you should be able to answer all the questions. Any suggestion? In YouTube also I have done many concepts, but the total concept cannot be covered in YouTube, but most of the many concepts I have covered in YouTube. I can't suggest you to just watch YouTube lectures, because that will not cover everything. So fine, you can contact me on my Telegram. Okay, you can just message me, I can help you definitely. Okay, we'll figure out something. Okay, right. Very good. So now what is left is probability of error calculation. So whatever we have discussed in today's session, shall we stop it here? We have talked about MapML criteria also. Tomorrow is a practice session, but we'll talk about probability of error calculation first. Probability of error calculation. Once we talk about probability of error calculation, I'll summarize everything, and we'll make everything that we have discussed in today's class much more easier. Just by looking at that butterfly diagram, you will be able to answer everything. Every question that is possible from this diagram, you will be able to answer. They can ask you the decision criteria, they can ask you probability of error, probability of correctness. Okay, all of them we can easily answer very, very easily just by looking at butterfly diagram. Okay, so I'll just show the easiest way in tomorrow's session. Okay, right then, so we'll stop at this place and we'll meet in tomorrow's session. So I've given some small homeworks. If you have done those homeworks, you can type it in the comment box, and tomorrow there will be a session again at 8 p.m. which is a continuation session for this. So we'll talk about probability of error calculation first, and we'll talk about the easier procedure first, and then we'll practice the possible questions from this topic. Okay, fine guys, good night, take care, bye bye, see you, we'll meet again tomorrow.